Something is missing. Out in the vast, dark expanse of the cosmos, something that should be there has simply vanished. Imagine a galaxy, a swirling city of billions of stars, gas, dust, all held together by an immense gravitational anchor at its center. This anchor, a supermassive black hole, is the heart of its galaxy. But in a distant galaxy known to astronomers as Able 2261, that heart is gone. We look to the center, where the brightest cluster of stars should be, where the gravitational pull should be strongest, and we find nothing. A void. It's a cosmic crime scene, and the mystery has baffled scientists for years. Where did a monster black hole, billions of times the mass of our sun, go? This question is not just a curiosity. It strikes at the very core of our understanding of the universe. The laws of physics, as we know them, are supposed to be absolute. Objects with mass don't just disappear without a trace. The search for this missing black hole led scientists on a hunt that would ultimately test the very limits of Albert Einstein's most profound theory. Be sure to watch until the end so that you don't miss anything from our journey. I would love to hear from you in the comments below. Before we can understand the kick, we must first understand the stage on which this cosmic drama unfolds: space-time. Think of the universe not as an empty box filled with things, but as a giant, stretchy fabric. This is space-time. Every star, every planet, every person, you and me, we all create a small dent in this fabric. The more massive an object is, the deeper the dent it makes. What we feel as gravity is simply the curvature of this fabric. A planet orbits a star, not because of a mysterious invisible rope, but because it's rolling along the curve in space-time, created by the star, like a marble circling a bowling ball placed on a trampoline. This was Einstein's genius in his theory of general relativity. Now imagine something far more massive than a star. Imagine an object with so much mass crammed into such a tiny space that its dent in the space-time fabric becomes bottomless. This is a black hole. Its gravity is so intense that the fabric of space-time curves down into an infinitely deep well. Once you cross its edge, the event horizon, there is no escape. The slope is too steep. Not even light, the fastest thing in the universe, can climb back out. That is why we call them black holes. They are the ultimate cosmic prisons, swallowing everything that gets too close and revealing nothing of what lies within their mysterious depths. They are the true monsters of the deep. For a long time, black holes were purely theoretical, mathematical ghosts, haunting Einstein's equations. We couldn't see them directly, so how could we prove they were real? The answer came not from seeing, but from hearing. Einstein's theory also predicted that when massive objects move and accelerate through space-time, they don't do so quietly. They create ripples in the fabric, like a boat moving through water. These ripples are called gravitational waves. They are minuscule distortions of space and time that travel outward from their source at the speed of light, carrying with them the story of their violent birth. They are a cosmic symphony, playing the music of the universe. For decades, these gravitational waves were too faint for us to detect. We were deaf to the universe's most dramatic concerts. But that all changed on September 14th, 2015. On that day, two incredibly sensitive detectors felt a tremor, collectively known as LIGO, the Laser Interferometer Gravitational Wave Observatory. It was a tiny vibration, a distortion of space-time smaller than the width of an atomic nucleus, but it was unmistakable. For the first time in human history, we had heard a gravitational wave. The Symphony of Spacetime was no longer silent. But what kind of cosmic cataclysm could create such a powerful wave? The signal that LIGO detected on that September morning was a sound unlike any other. It was a chirp, a sound that rapidly increased in frequency and volume before abruptly stopping. Scientists had a suspect for what could make such a sound: the collision of two black holes. Imagine two of these cosmic titans, each dozens of times the mass of our sun, locked in a gravitational dance. They have been orbiting each other for millions of years, perhaps eons, slowly spiraling closer and closer together as they radiate away their energy as gravitational waves. This is a black hole merger, one of the most violent events the universe has to offer. As they get closer, their dance becomes faster and more frantic. They whip around each other at speeds approaching the speed of light, churning the fabric of space-time into a tempest. The gravitational waves they emit become stronger and higher in frequency, like an ice skater pulling their arms in and spinning faster. The two event horizons begin to stretch and distort. In the final fraction of a second, they touch, and in a flash of gravitational energy, merge into a single, larger black hole. The universe has just created a new, more massive monster. The energy released in this final moment is almost beyond comprehension. For a brief instant, the merger can outshine all the stars in the observable universe combined. But this energy is not light. It is pure gravitational energy, a tsunami of space-time ripples flooding the cosmos. The resulting new black hole is not simply the sum of its parts. A portion of the original mass, equivalent to several suns, is converted into energy. According to Einstein's most famous equation, E equals mc squared. This is the energy LIGO detected as that final, powerful chirp. When the merger finishes, the new black hole quivers like a struck bell. It sheds the last of its energy in a final ring down. As the ringing fades, the new black hole settles into a perfect sphere of darkness. Or does it? Here is where the story takes a truly strange turn, leading us back to the mystery of the missing black hole in Able 2261. Einstein's theory of general relativity predicts that a black hole merger is rarely a perfectly symmetrical event. The two original black holes are unlikely to have the exact same mass or the exact same spin. One might be slightly heavier, or one might be spinning faster than the other. This imbalance, however small, has a monumental consequence. When they merge, the gravitational waves they blast out are not sent equally in all directions. More energy is radiated in one direction than in another, like the exhaust from a rocket engine. This asymmetrical blast of gravitational waves creates a recoil. According to Newton's third law, for every action, there is an equal and opposite reaction. If you blast trillions of suns worth of energy in one direction, the object that created the blast must be pushed in the opposite direction. This push is called a kick. The newly formed black hole, born from the violent union of its parents, is literally kicked away from the site of the merger. It's a game of cosmic billiards where the cue ball is a ripple in space-time, and the target is a monster with the mass of 100 billion suns. The speed of this kick can be enormous. Theoretical models predicted that these kicks could reach speeds of hundreds of thousands, or even millions of miles per hour. That's fast enough for a black hole to escape the gravitational pull of its own star cluster, or in the case of a supermassive black hole merger, fast enough to be ejected from the center of its galaxy entirely. This provided a perfect, elegant solution to the mystery of Abel 2261. Perhaps its supermassive black hole wasn't missing at all. Perhaps it was kicked out of the galactic core by a powerful merger event eons ago, and is now wandering silently in the galaxy's halo. But for all its elegance, this was just a theory, a beautiful mathematical prediction. No one had ever directly observed a black hole being kicked. We had detected the gravitational waves from the merger, the action, but we had never seen the reaction, the newly formed black hole recoiling from the blast. Measuring this kick seemed impossible. We can't see the black hole itself, so how could we possibly track its motion across millions of light years of space? To prove Einstein right once again, scientists would need to find a new way to listen to the story being told by the gravitational waves themselves. The challenge was immense. How do you measure the velocity of an invisible object a billion light-years away? You can't use a cosmic radar gun. The key, scientists realized, was hidden within the gravitational wave signal itself. Specifically, in the ring-down phase, the final moments after the two black holes have merged. In spiral, merger, ring-down. As the newly formed, distorted black hole settles into its final spherical shape, it emits a final burst of gravitational waves. Think of it like the sound a bell makes after being struck. The tone and the way the sound fades away can tell you a lot about the bell. Its size, its shape, and even if it's moving. For a black hole, the ring down contains information about the final black hole's mass and about its spin. But theorists like Stephen Hawking predicted something more subtle. If the new black hole was moving, if it had received a kick, that motion should be encoded in the waves. The motion would cause a slight shift in frequency and amplitude, a gravitational Doppler effect, like an ambulance siren, changing pitch as it passes. The effect is incredibly small, nearly lost in the noise of the main signal. So, scientists re-examined past merger data with a more sophisticated lens. They focused on one event detected on January 29, 2020, GW20, 0129, two black holes, one about 58 times the mass of the Sun, the other about 24 times the mass of the Sun. They merged to form a roughly 75 solar mass black hole. The signal was strong and relatively clear, ideal for a deep forensic dive. The team at the Rochester Institute of Technology led the analysis. They couldn't rely only on the main mode. They needed higher harmonics or overtones. A musical note has a fundamental tone and several quieter overtones. Likewise, a ring down is a complex mix of frequencies. Theorists predicted the kick's signature would be most apparent in those higher frequency overtones. The hunt began to isolate these faint whispers from the merger's roar. The team developed a new analytical model, a sophisticated piece of code designed to sift through the complex waveform of GW 200129, searching for the telltale signature of recoil. They were looking for a specific frequency shift and an amplitude modulation only caused by a massive object moving at high velocity. It was like trying to hear a single person's whisper in the middle of a roaring stadium. The model had to compare the observed data against two competing hypotheses. One, where the final black hole remained stationary, another, where it was kicked away from the collision site. The data would decide which story was true. After months of painstaking analysis and running supercomputer simulations, the results came in. The evidence was overwhelming. The model that included a recoil, a kick, fit the GW20129 ringdown far better than the model without one. Side-by-side comparison graphs observed GW200129 with kick model fit or no kick model mismatch. The data showed a clear preference, with a confidence level of over 99% for the scenario where the newly formed black hole was in motion. For the first time, humanity had not just inferred a kick, but directly measured its effect within a gravitational wave signal. They had witnessed the equal and opposite reaction Einstein's theory demanded. The measurement was astonishingly precise. The analysis revealed the new 75 solar mass black hole was kicked at approximately 1,542 kilometers per second. That's over 3.4 million miles per hour. Put another way, New York to Los Angeles in under 3 seconds. This speed could let the black hole escape even the most massive star clusters. The prediction was no longer just a prediction, it was observed, measured, and quantified. This breakthrough was a triumph of scientific ingenuity. It combined advanced theoretical physics, cutting-edge data analysis, and the incredible sensitivity of the LIGO detectors. It was a testament to looking at old data in new ways, asking new questions, and relentlessly pursuing subtle clues hidden within the noise. The team measured the velocity of an invisible object over 1 billion light-years away using only the faint ripples it made in the fabric of space and time. A cosmic mystery had been solved, and two of the greatest minds in physics were proven right once again. This discovery is a stunning confirmation of Albert Einstein's theory of general relativity, 100 years after he first proposed it. Einstein's equations predicted that gravity was not a force, but a curvature of space-time, and that this curvature could lead to the most extreme phenomena imaginable. The idea that merging black holes could generate such a powerful, directed blast of gravitational waves that it would kick the resulting object across the cosmos was one of the theory's most bizarre and untested predictions. The measurement of the kick from GW200129 moves this idea from theoretical possibility to observed reality. It shows, yet again, the incredible predictive power of Einstein's vision. The discovery also honors the legacy of Stephen Hawking, a pioneer in our understanding of black holes. Hawking's work on black hole thermodynamics and the nature of the event horizon helped lay the groundwork for understanding the ring-down phase of a merger. His insights, along with those of many other physicists, led to the prediction that information about the final black hole's properties, including its motion, would be encoded in the ring-down's gravitational waves. This measurement directly validates those theoretical models, proving that the complex mathematics describing black holes reflects the universe we live in. What this means is that our model of the universe works, even in the most extreme environments. The place where gravity is strongest, where time and space are warped to their limits, is exactly where general relativity passes its most stringent test. This gives us enormous confidence to use these theories to explore other cosmic mysteries. If the theory works for black hole kicks, we can be more certain it works when describing the Big Bang, the expansion of the universe, the nature of dark energy. More than confirming a theory, this measurement opens a new window into the universe. We have developed a new tool. By precisely analyzing the ring-down of future gravitational wave events, we can create a census of black hole kicks. We can study how the kick velocity depends on the masses and spins of the parent black holes. We can begin to map the journeys of these rogue black holes as they travel through intergalactic space. We have moved from simply detecting mergers to performing detailed astrophysics using gravitational waves to probe the dynamics of the most violent events in the cosmos. The confirmation of black hole kicks has profound implications for the life cycle of galaxies. Most large galaxies are thought to have a supermassive black hole at their center, including our own Milky Way. These central black holes are not just passive residents, they actively shape their host galaxies. They influence star formation. They shape the overall structure of the galactic core. But galaxies don't grow in isolation. They grow by merging with other galaxies. When two galaxies merge, their central supermassive black holes will eventually find each other, sink to the new center, and merge. Now, confirmation of powerful kicks makes this picture much more complicated and dynamic. If a merger gives a significant kick, the new, more massive black hole could be ejected from the galactic center. It might be sent on a long, looping orbit through the galaxy's halo, or be flung out of the galaxy entirely, roaming the lonely void as a rogue object. This would leave the galaxy heartless, without a central black hole, dramatically changing its future evolution. This helps explain puzzling observations. We see galaxies like Able 2261 that appear to be missing their central black hole. We also see galaxies where the central black hole is offset from the true galactic center. These are potential smoking guns of past merger kicks. Kick theory also explains the relationship between black hole mass and galaxy mass. If kicks are common, they preferentially eject smaller black holes, leaving only the most massive to anchor the biggest galaxies. A kicked supermassive black hole, even if bound to the galaxy, can have a dramatic impact. As it travels, its gravity would disrupt star clusters, fling stars out of the galaxy, and carve a path of gravitational chaos. It could even trigger bursts of star formation as it plows through dense gas and dust. Understanding kick frequency and magnitude is critical to modeling galaxy formation and evolution. The fate of galaxies, it turns out, can be decided by a single violent kick. The measurement of a black hole kick from the event GW 2001-29 is a landmark achievement. It confirms a century-old prediction of Einstein's theory of gravity in the most extreme setting imaginable. It validates the theoretical work of Stephen Hawking and countless other physicists on the nature of black holes. And it solves a long-standing astronomical puzzle, providing a mechanism for how a galaxy can lose its central supermassive heart. We have transitioned from asking if black holes get kicked to asking how hard and how often. We have opened a new chapter in the study of the dynamic and violent universe. A theoretical prediction is made based on a mathematical model of the universe. For decades, it remains an untestable idea. Then, new technology, in this case, the incredible LIGO detectors, provides a new way of observing the cosmos. Scientists use this new technology to hunt for evidence, developing ingenious new methods to extract a tiny, hidden signal from the noise. The evidence is found, the theory is confirmed, and our understanding of the universe takes a giant leap forward. It's a story of human curiosity, ingenuity, and perseverance. But this answer only leads to more questions. How many rogue black holes are wandering between the galaxies? Could one be passing through our own Milky Way's halo right now? What happens to a galaxy that loses its central black hole? Does it slowly fall apart? Or does a new one eventually grow in its place? Each new discovery reminds us that the cosmos is more dynamic, more violent, and more surprising than we ever imagined. We have listened to the echoes of a cosmic collision a billion light years away and learned something fundamental about the laws of nature. It's a humbling reminder that even the most massive and powerful objects in the universe must obey the simple principle of action and reaction. The universe is a place of unimaginable violence and sublime order, all playing out according to a set of rules we are only just beginning to fully comprehend. Ready to dive deeper into the matrix? Watch the next video to see just how deep the rabbit hole goes. And since you made it this far in our journey, be sure to share your experience in the comments below. And as we continue to listen to the Symphony of Spacetime, what other secrets are waiting to be heard?